Hi ladies and gentlemen, in this video we will understand the basic concepts of source coding, and in the same video we will see about a pulse code modulation. So this is a way we convert a source symbol into a binary code for digital transmission. So let me start with that presentation. So the speech is organized into your learning outcomes, then the meaning of source coding, then the type of waveform coding that is included in your syllabus, that is a temporal waveform coding. Then the first method of source coding, that is a pulse code modulation, which is very popular in digital telephony. Then the Nyquist sampling theorem for low pass signals, the quantization, the effect of quantization, that is a quantization noise, and summary of understanding. What you will learn in this video, or you will learn the meaning and types of source coding. Then you will learn about sampling and reconstruction of low pass analog signals. Then you will learn the block diagram of a PCM coder. Then you will learn the transfer characteristics of uniform quantizers like a mid-rise quantizer and a mid-thread quantizer. Then you will learn the noise due to quantization, and you will compute the noise power in quantization noise power and the signal to noise ratio. Then you will understand the rise in signal to noise ratio with encoding. So source coding is a conversion of an analog source into digital codes. That is the idea. So often in discrete communication systems you work with symbols. So whatever we want to communicate, they are put into a finite number of symbols, and the symbols are then encoded and transmitted through the channel. Now, for example, in India, in driving, whatever you want to communicate to a fellow driver, they are mapped into 5 or 6 symbols. Like if you turn your, or if you stretch your right hand, then it means that you want to turn to the right. So the driver behind you and drivers coming in the other direction, they know that you want to make a right turn, and they slow or adjust their vehicle accordingly. So these 4 or 5 symbols are mutually agreed upon, and they respect that. So whatever each driver wants to communicate to the others, they are encoded into 5 symbols. So likewise here, instead of transmitting the whole signals, you can send some samples that are encoded in binary format. So that's the idea of source coding. There are 3 methods. That is a temporal waveform coding, in which you look at the signal waveform in the time domain, you sample it, quantize, and send it. That is the one that is coming in the syllabus. Then there is a spectral waveform coding, which is a frequency domain counterpart of the first method. That is, in the frequency domain you do the coding. That's a rather less popular one. Then there is a model based source coding, in which instead of sending the source symbols, you make a model of the source symbol and you code the model, like a transform coding, etc. belong to this group. Anyway, the present study in your syllabus is focused on temporal waveform coding, the first method. So these waveforms are sampled, quantized, and encoded to binary signals. So the various methods are the pulse code modulation, it is pulse code modulation, the differential pulse code modulation, delta modulation, adaptive delta modulation, adaptive PCM, etc. The pulse code modulation is a very popular coding in digital telephony. The analog source signal, such as speech signal, is sampled at the Nyquist rate. So how many samples are to be sent? So if I have a speech signal, how many samples should be taken? It was a question. That question was answered by Shannon and Nyquist, and that resulted in the Nyquist sampling theorem. Probably you have learned that in the signals and systems course. Then the magnitude, the sampled thing has a different magnitudes, then the magnitudes are quantized into some fixed levels. Then the quantized samples are then encoded to binary. So when you look at the Nyquist theorem for low-pass signals, suppose I have an analog signal that is band limited to FM, then if this is sampled at more than a rate, or at or more than a rate, that is, if the sampling frequency is greater than or equal to twice of FM, then the original signal can be reconstructed. Okay. If I take, that means if I take 2 or more samples out of my message period, then the original message signal can be reconstructed. How do I reconstruct that signal? That is with an ideal low pass filter. Okay, if I pass these samples at the receiver, if I pass these samples through an ideal low pass filter with impulse response sine 2 pi bt by 2 pi bt, I can reconstruct the original message signal, and that formula is called the Whittaker formula. So sampling above Nyquist rate, that looks like this. Suppose I have a sinusoid here. This blue one is an analog sinusoid, and these red ones are actually the samples taken. What the Nyquist theorem says is if you take 2 samples out of a period, that is from here to here, if I take 2 samples, I can reconstruct the signal. If these samples are taken at the midpoint, it's okay. If these samples are taken here and here, still then I can reconstruct that. Then where can I not reconstruct this? That is, if I take these samples at the 0 crossings, then I get zeros only. Then I cannot reconstruct that. That is, if the sample falls here, see, if I take a sample here and one sample here, I still can reconstruct the signal. But if I take these samples here at the 0 crossings, well, I will be sampling at 2 FM, but if I take at these 0 crossings, then I cannot reconstruct that signal. That is why there is a greater than sign. Fs should be greater than or equal to 2 FM. So typically 4 times or something, that is more than enough. There is no point in pushing it further, like more than 4 or something. It is not, there is no great advantage in that. Now if you look here, you can see that I have taken 3 plus 3, 6 samples out of a period. 1, 2, 3, 4, 5, 6 samples out of a period. And then it results in a discrete signal like this red signal. It's a discrete signal, discrete in time, but may not be discrete in magnitude. This is discrete in time. So what is the frequency of this one? Frequency of such a discrete signal is measured in that is a number of cycles per sample, or inverse of the number of samples per cycle. So frequency of a discrete signal is measured in terms of the number of cycles per sample, or which is the inverse of the number of cycles per sample, number of samples per cycle, I'm sorry. Now here I have got 6 samples out of a period, so its frequency should be 1 by 6. Okay, so its frequency is 1 by 6, which is the maximum frequency, that is half. When I take 2 samples out of a period, that is a Nyquist rate. If I take 2 samples out of a period, then its frequency will be 1 by 2 cycles per sample. Okay, so the frequency of a discrete signal, that is bounded between minus half and half. Okay, any frequency outside this band will be equal to a frequency inside this band. While in the analog domain, the frequency is measured in hertz, that is the number of 0 crossings in a second. That will vary from minus infinity to plus infinity. Okay, so this is how I sample these things above the Nyquist rate. Now, how do I get this blue signal out of this red signal? That is, this red signal, these are actually short impulses. No practical system will process these impulses. So there is only one system with which I can reconstruct my blue analog signal back, that is called an ideal low pass filter, with the impulse response a sinc function, that is sine 2 pi bt by 2 pi bt. Okay, this b should be fairly more than your fm. Okay, slightly more than you, or else there will be aliasing. So then if I pass this samples here, I will get an approximation of this xt, or your original signal. Now this is what is happening. So this is a signal, this analog signal. I sampled it at some rate above the Nyquist rate. Then this is my this I have to reconstruct this blue signal from this signal. So I have to pass through a filter whose impulse response look like this. This is sine 2 pi bt by sine 2 pi bt. Okay, this is of the form sine 2 pi bt by 2 pi bt, where this b should be 1 by 2. Here the sample interval is 2, okay, t. So this b should be equal to 1 by t. So we will see this with a sinusoid here. This is what is actually happening. This is how I reconstruct this sinusoid. See, originally I had this sinusoid. Okay, this black curve or deep blue curve. This is a sinusoid. Here I have taken 4 samples out of that, 5 samples out of that. Here there is one sample here, 1 2 3 4. Yeah, here there is a sample 1 here, 1 2 3 4 5. Okay, there's a sample here, 1 2 3 4 5. Okay, the sampling rate is 5 times. Okay, for 5 hertz. Now these are the samples I have got. This is one sample here, this is another sample here, this is a sample here, this is a sample here. Now, how do I get this sample, get this original signal, this deep blue curve from these samples? That is, I have to convolve with a sinc function like this. Okay. Now, when I convolve this sinc function, when I convolve with this 0 point, nothing happens. Okay. When I convolve my sinc function with this red curve results. Okay, this red curve results. Now this tapers off like this to infinity. Up to infinity this goes, but the magnitude tapers off. Now this is the first thing. Now this is the second impulse. So when convolved with a sinc function, that sinc function looks like this green curve. Okay, it comes this way. It comes this way. Okay, it comes this way. And here is my another one. So if I do this, this will be something like this. Okay, now here is a curve coming here, this in the negative direction. Okay, and here I have a fourth sinc function happening here. Now this goes on. When I do the convolution with the ideal low pass filter, this go on like this. Now if you look at the peaks of these sinc functions, it will give you an approximation of your, it will be an approximation of your original sinusoid. Okay, this is how you do the interpolation with the Whittaker formula. I will show you a code which I have copied from a website. This is not written by me, but I actually copied from a website. Yeah, this is a reconstruction thing. You can see here the signal frequency is 1 hertz and FS, the sampling frequency is 5 hertz. That is why you saw 5 samples out of a period. And here I have defined a time from -1 to 1 with 100 point with the Lin space function. And here the sample points are 5 times this, that is 1 by Fs. Okay, from -1 to -1 by Fs to +1 by Fs. And the number of coefficients is the number of, total length of this TS. And here I put a for loop, and here this SM is your this is your interpolating function, that is sine 2 pi bt by 2 pi bt. Okay, so these samples are here, they are multiplied, but this is a sine pi k fs. These are the samples, actually they are multiplied by the sinc functions and they are added together. Okay, then we plot this, so you can see this. Okay, so then there are some plot functions. I will run this code for you. Now you can see that the sampling happening at 5 times 5 hertz. Original signal is 1 hertz, and original signal, the analog signal is 1 hertz. So you take 5 samples out of a period, so the sampling frequency is 5 hertz. And here you can see the sample values coming here. This is the first sample. This is a sync function happening here. This is the next sync function that is happening. Now you can see the cumulative effect. Okay, this is a curve I showed you. So if I follow the peak of these sync functions from here, I come here. Okay, I come here. Okay, I go this way, I come here, I follow this way. If I follow the peaks of these sync functions, I'll get an approximation of my original sinusoid. This is how reconstruction is done with the Whittaker formula. Let me go back to my presentation. So this is how the reconstruction is done. Often people miss this reconstruction part when they discuss the sampling theorem. The reconstruction, the Whittaker formula part is part of the sorry, it is part of it is part of the sampling theorem. Now we come to the first source coding method called pulse code modulation. This is a very popular method in digital telephony. Even though the name is modulation, says a word modulation, it is not a modulation method, it's a source coding method. It's a way in which you convert a source symbol into binary codes. Okay, modulation is a totally different thing. The word modulation is there that it obeys modulation theorem. In the sampling process, there is during the sampling process, this obeys the modulation theorem. That is why the name. It is neither an analog modulation method nor a digital modulation method. It's a source coding method. Now what happens is I have a speech signal or a continuous time signal. This is subjected to sampling at above the Nyquist rate, at or above the Nyquist rate. So this xnt, what comes out of the sampler is xnt, that is a discrete time signal whose magnitude may not be quantized. Okay, so then the magnitude is also quantized. Then it becomes then I will have a finite number of magnitudes only. Okay, I have a finite number. Suppose I have 8 levels in a signal, or may have 16 amplitudes in a signal. Okay, so those 16 amplitudes I can encode with some binary digits. Like I can, if there are 16 values, I can use a 4-bit code, say 000 to 111. Okay, 16 values I can encode that way. Yeah, if there are 256 values, I can encode with 8-bit values. So what comes out of this encoder are the bits. So these bits are actually representation of this speech signal. This is the way the PCM system works. Now, as for the sampling, you have understood the sampling and reconstruction. Then the sampled signals, then they are converted to a finite set of amplitudes. Say if I have 16 possible values, then I can encode with the 4 bits. That is called a quantization. That is a magnitude quantization. So magnitude quantization is there in all practical systems, because most practical systems have a finite register length, so automatically it will be truncated somewhere. So, but you put it to some number of some possible levels that are powers of 2, so that I can encode with binary bits. So if I have 16 possible values, then I can encode with 4 bits. If I have 256 possible levels, then I can encode with 8 bits. In a uniform quantizer, the separation between the levels is called step size. Okay, that's called a step size. That's a constant. The steps are constant. Say this quantization is very straightforward. If I have a value like 7.7586, I can quantize it to 7.76, or I can quantize to 7.8. So I set that level, I set the step size in such a way that all step size are constants. Such a quantizer is called a uniform quantizer. So this is how the characteristics say these are the input values, these are the output levels. So input levels, there may be continuum of input levels, but output levels, they will be discrete in nature. So say from 0 to some value, say delta by 2, it will all be kept at 0. Say and minus delta by 2 to delta by 2, all values will be kept at, output value will be 0. Then from some delta by 2 to some 3 delta by 2, it will rise by another step, it will be another delta. After 3 delta by 2 to 5 delta by 2, it will be 2 delta, 3 delta, that way. Okay, and the negative also. This is called a mid-thread quantizer, meaning that there is a thread at the low end, that is for 0. From minus delta by 2 to delta by 2, the value is kept at 0. That is, for small amplitudes of the input level, the quantizer output will be 0. I have another way, that is a mid-rise quantizer, in which it behaves like this. At 0, it can be either at plus delta by 2 or at minus delta by 2, and other steps are of equal dimension. Okay, they are all of size delta. So this one is a mid-thread quantizer, and this is a mid-rise quantizer. Now, when you do this quantization magnitude, there is an unavoidable quantization noise. Say if I truncate 7.755 into 7.56, I have an error of 0.005. Okay, so that small error will be there. So the absolute value, if I consider the absolute quantization noise, that will be xn, the original discrete signal, discrete in time, but continuous in magnitude, minus quantized value of that one. In the practical example, it may be this may be 7.755, this may be 7.6. There's a 0.05 difference. That 0.05, that is my quantization noise. Now, this quantization error is a random variable that is uniformly distributed in the interval minus delta by 2 to delta by 2. It can be anywhere. If this value is there, it can be either here or here. Okay. If some value here, it can either fall into this or fall into this with equal probability. So this step size is delta. So that error is uniformly distributed in the interval 0 delta or minus delta by 2 to delta by 2. So this PDF of the probability density function of this quantization noise, I denote by FQQ, that is 1 by delta in the range minus delta by 2 to delta by 2. Okay, minus delta by 2 to delta by 2. The area should be 1, that's why it is 1 by delta. Okay, this step is delta, this height is 1 by delta, so the area under this curve, that is a 1. Okay, that validates a PDF. Everywhere else it is a 0. So this is the shape of your uniform PDF. This is the PDF of the quantization noise. Now I need to compute the noise power. If I have a quantization noise, I am interested in the quantization noise power and the signal to noise ratio. So I can compute it by computing the variance. Already we computed the second order moment. So this sigma q square, this is the variance of the quantization noise. That is a power, signal power or noise power, that is minus infinity to infinity q square fqqq dq. You know that this fqqq varies from minus delta by 2 to delta by 2. So my limits are changed from minus delta by 2 to delta by 2. It is q square, and fqqq during this interval is 1 by delta dq. So it is 1 by delta q cube by 3 from minus delta by 2 to delta by 2. So this becomes delta square by 12. So that is a quantization noise power, delta square by 12. And now I can relate this with the number of bits used for encoding this. Say for example, if my input signal is a sinusoid with the amplitude say V, then the step size will be 2V by L, because one side amplitude is V, so peak to peak amplitude is 2V. Suppose I have L levels. If I divide this 2V into say L equal levels, then this delta will be 2V by L, because I have L levels and the total span is 2V, so the delta is 2V by L. And this L is actually 2 raised to R, where R is the number of bits used to represent a level. Because say suppose L is 16, that is 2 raised to 4. I can represent 16 levels with 4 bits. Okay. If it is L is 256, then R is 8. Okay. R is 8. I can represent L 256 levels with 8 bits. Okay. So R is the number of bits. So that will be, now that will be this sigma q square, or the quantization noise power will be 4V square by 12 into 2 raised to R. Okay, this is my delta square by 12. Okay, and this is the noise power. This is a quantization noise power. I am interested in the signal to noise ratio, which is the ratio of the signal power to the noise power. The signal power is V square by 2. sorry, the signal power is V square by 2. So the signal to noise ratio is V square by 2 divided by 4V square into 12 into 2R, this 2 raised to R. This becomes 3 by 2 into 2 raised to 2R. 3 by 2 into 2 raised to 2R. This, when I express in dB, when I express this in dB, this becomes 10 log 3 by 2, 10 log 3 by 2 plus 20 log 2 into R. So this value become 1.76 plus 6.02 R. R is the number of bits. Suppose I am not using any encoding, this R will be 0. So the base signal to noise ratio is 1.76. Okay, the base 1.76. That is, if I don't use any encoding, any binary encoding, that basic SNR will be 1.76. Okay. Now, if I add one bit, the signal to noise ratio rises by 6.02. That is, if I move from R bits to R plus 1 bits, the signal to noise ratio of PCM rises by 6 dB, which is quite a big number. This you have to understand very thoroughly. When the number of bits increases from R to R plus 1, the signal to noise ratio rises by 6.02 dB. This is the advantage in using digital systems like compact disc, video disc, etc., optical disc. This is how this SNR rises. So what you learned is, you learned the meaning and types of source coding. Then you learned the sampling and reconstruction of low pass analog signals. Then you learned the block diagram of a PCM coder. Then you understood the transfer characteristics of uniform quantizers like the mid-rise and mid-thread quantizers. Then you learned the quantization noise and computed the noise power and signal to noise ratio. Then you understood the rise in SNR with the encoding. And that's the end of this presentation. I thank you all.